Okay, so we're going to just start this discussion on multinomial experiments by just starting with a review of a binomial experiment. And we're going to actually do a hypothesis test for a proportion in the context of a binomial experiment. And remember, whenever we work with categorical data, we're talking about proportions. Okay, so binomial, there's just a single proportion, the proportion of some sample that was a success. And then we're gonna learn a new way to do the same hypothesis test, and you'll see that the new way is equivalent to the old way. But then the advantage of the new way is that it allows us to have more than two categories. So you can do this test on binomial experiments, but you can also do this test, the same test, on multinomial experiments. And it's equivalent to what you've learned, okay? But it sort of builds on it, and it's just more flexible, okay? And these tests are called chi-square. So the Greek letter here looks like an X, but it's a chi. Okay, so that's a Greek letter. And honestly, I don't know which of our letters that this is most analogous to. Sometimes I think it's like a K, but I think it's more of an uvular, but meaning you use your uvula to say it, but I honestly don't know. Okay, so let's get to work here. So section 11.1, again, it's on multinomial experiments and goodness of fit, which is a crazy term. So in this lesson, we consider multinomial experiments. Multinomial experiments are like binomial experiments. There are n independent trials, but instead of 2 outcomes per trial, we allow 2 or more outcomes per trial. A binomial experiment is just a special case of the multinomial experiment. We begin with a binomial experiment in the context of a hypothesis test for a single population proportion. Okay, so this is under asthma incidence among youth. The Statistical Abstract of the United States reported that in 2008, approximately 17% of male youth were told they had asthma. A researcher in Florida wants to compare this to the proportion of male youth in that state who have asthma. So they're looking at just Florida and comparing it to the 17%, which is the nationwide statistic. Okay, it says in a recent random sample of 400 male youth in Florida, 88 responded that they had asthma. This sample is the result of a binomial experiment. Each trial has 2 outcomes. Either you have asthma, which is a success, and not a good one, or no asthma, which is a fail. Okay. At the 1% level of significance, we want to investigate the claim that asthma among male youth in Florida is different from the national figure. Okay, any questions? So that's going to be a two-tailed hypothesis test. So it says this is a hypothesis test about a single population proportion. What are the appropriate null and alternative hypotheses? Okay, so you did this on your last exam. The null hypothesis about a proportion has to be p equals something, and the alternative has to be p is less than, greater than, or not equal to that number. Okay, and it says, if you look at the very last statement here, it says that asthma among male youth in Florida is different. So that's a not equal claim. Different from the national figure, and the national figure is the 17% that was reported in this statistical abstract that they're talking about. Okay, any questions? So P is not 0.17. That's the 17%. My screen's frozen. Hang on. There we go. Or P equals 17%. So again, this is one you did on your last test. Any questions? Okay, so you may remember this. The criteria for normality require that the expected number of successes, n times p, is at least 10, and the expected number of failures, n times 1 minus p, also has to be at least 10. So the expected number of successes, np, by the way, this should be nq up here. You may remember 1 minus p is the same as q. So np is, so there are 400 kids, I think. Yeah. 400 times p, which we assume is 17%. That's our null hypothesis. Grabbing a calculator here. Let me get it. 68. Okay. And then remember Q is 1 minus P. So 1 minus 17%. I think it's at 83%. 83% of the kids did not or would not have asthma if the null hypothesis is true. So when we do NQ, this is 400 times 0.83. So I'm guessing this is going to be 332 because these have to add up to 400. The kids with asthma, the expected kids with asthma, and the kids without asthma. Expected should add up to 400 because there's 400 kids. Okay. Now, as long as these are both greater than or equal to 10, then the criteria are satisfied. Okay, any questions? Everybody okay? Okay, so sample proportion, remember that's p hat. So that should be x over n, the successes over the sample size. Now that's where you have to go back. There were 88 kids with asthma in the sample. Again, those are the successes, so that's x. And of course, as we said, n is 400. Okay, so x over n is 88 over 400. Is that right? No. What do you get? 20%. And that's, and remember that we're claiming that the population proportion is different from 17. This is 22. So, but this is a sample. And so the question is that significantly different from 17? I don't know. I need to find out how many standard errors of difference there is. Okay, any questions here? All right, so once you have all that, you can do the z-score for the test stat. So z is p hat minus p over the square root of pq over n. Don't forget the q is 1 minus p, so I've got some cases here where I'm saying 1 minus p, which is the same as q, so please forgive that. Correct formula, you know, both of these formulas work, but the one you recognize is the one I just wrote. Okay, so anyway, p hat was 0.22, p is 17%, 0.17. Okay. And then over p, 0.17 times q, 0.83, I think, over n. And it's crazy, they want us to keep 5 places after the decimal here, which is extraordinarily precise. But the goal here is we're going to teach you a new type of test. It's called the chi-square. Remember that Greek letter chi up here that I was showing you? This test is called chi-square, and you'll see why it's called chi-square. But we want you to see that these tests are equivalent, and that's why we're going to be super precise here. So let's go ahead and if you don't mind, do that computation. I'm going to try it as well. All right, 2.66217, exactly what I got. Okay, and I think I'll draw a little picture of this. We're going to, again, be pretty precise when we get our p-value. Okay, so z distribution. Let's lock down our 2.66217. Okay, and this guy. And I think I'm going to boot up my my p-value calculator real quick. So I don't know if you remember, but I've posted some of these in Canvas. So it's on Desmos. So it's in my account. So I think if I just go into my account, oops, I did not mean to do that. Forgive me. Just need to log in is what I need to do. Okay, it's not recognizing me as me. Okay, and so somewhere in here I've got my z, my normal distribution p-values. So all I have to do is type in what we got. It was 2.66217, I think is what we're using. So 2.66217. Whoa, that's wrong. 17. Okay. And I think we can say 0.003882 for the area of the tail. You guys see that? I'll just say 0.00388. Okay, any questions? Oops, screen's frozen, hang on. There we go. Okay, I'm just gonna pause for a second, see if you guys want to ask me any questions. So those are the two critical computations in a hypothesis test. Pretty much if you get those two things right, you know what you're doing. First, you gotta be able to interpret them. But that's a really small p-value. And let's look at our alpha here. 1% level of significance, I think you can see at the top here. So it needs to be less than 0.01, which it is. Okay. So critical value, bottom row of table A2. Let's skip this. No, I take it back because we're going to do critical values for the chi-square. It's good. We'll go with it. Bottom row of table A2, fine. Let me pull that up. Okay, so just to remind you, is this a two-tailed test? So I'm looking under two tails with a 0.01 alpha here. Okay, so the very bottom row there is a 2.576 critical value. Okay. That's where the z-scores are in that table. 2.576, fine. Oops, wrong one. And this is for alpha equal to 0.01. Critical that. Okay. Any questions? Okay, so with the null hypothesis, we remind ourselves the p-value was 0.003 something something 00388, which is less than 0.01, which is our alpha. Is that a reject or a fail to reject? Anything? What do you say? What do you say? Reject the null hypothesis. So reject the null hypothesis, support HA, sorry, H1. I hope I have explained to you that sometimes my other stats classes use HA, depends on the source material. So it's the same thing. Support H1, which had said that he is different from 17%. And that's all we're saying is the national figure for asthma is 17%, but they're saying it's different in Florida. As a matter of fact, they got 22% in a sample. So it seems like it's higher in Florida. Who knows why? All the pollen or the fungus in the air, I don't know. The spores, as they say. Okay. So our data support their claim. So that the proportion of male youth in Florida with asthma is different from the national figure of 17%. Okay. Anybody want to ask a question? You guys okay? So that's just like a review. Been there, done that. And so lovely to cover something you already know. And now we want to show you how you can get the exact same result with a chi-square test. So chi-square is used for categorical data almost exclusively. It has other applications that aren't used much. But the chi-square tests are usually these tests for multinomial experiments. Again, the multinomial experiment is where it's the same as binomial, but with more than two outcomes. But it works for binomial. So we're going to do a binomial experiment. So let's keep going here. So it says the Z statistic in the previous example works well for binomial experiments, but that's when there are only two outcomes per trial. When there are three or more outcomes per trial, things get more complicated, and the Z statistic doesn't allow for sample proportions for each outcome, so that's our problem. When there are two or more outcomes per trial, we can use a different test statistic. The statistic is called chi-square, okay, and that's the notation there for the Greek letter chi. Again, the closest I can think of is it's like it looks like an X, but I think it's more of a K, but I'm no expert. So of course it's not just chi, it's chi-square. Again, the square will make sense shortly. So we pronounce it as chi-square, and the formula for the chi-square statistic is always this thing that I've got here. Trying to get my screen to work better. Each outcome for the categorical variable, remember there's more than 2 outcomes. So each outcome in the variable corresponds to one term in the sum above, right? That big letter, that Greek letter sigma here, is a sum of a bunch of terms that look like this. But what are they? Well, E in the terms stands for expected frequency, and O stands for observed frequency for each possible outcome in the experiment. Okay, so the observed frequencies would be the number of boys with asthma and the number of boys without asthma. And the expected frequencies would be the averages. So you may remember in the binomial experiment, N times P was the average. Average is also called expected value. So when they say the expected frequencies, they're talking about the expected values, which are always N times P, or N times Q if you're doing the, N times P is for the successes, and N times Q would be the average number of failures. So these are all concepts we've talked about. It's just a totally different form for the computation. So it says, for the asthma incidence among youth example, each sample member falls into one of 2 categories. Either a teen has asthma or not. For the teens with asthma, give the observed and expected frequencies. So what's the observed number of teens with asthma? I think it was 88. Can't find it. Wait, it's up here. Dang, here we go. 88 kids had asthma out of 400, right? So just 88. And the expected frequency, remember, is N times P. That's just the formula for the mean from a binomial experiment. And again, mean is just another word for expected value. Okay? So N times P would be 400. And for P, remember we're using 17%. That's from our null hypothesis right here. Okay? So we're assuming it's true. So it's 400 times 0.17. Anybody? I think you 68. Okay, so it's observed and expected. That's the only thing. I mean, you got a null hypothesis that says it's 17%. So obviously you got to take 17% of 400 to figure out how many people you expect to have asthma. Right? You're assuming it's 17%. So this is totally obvious. And you can see this statistic, kind of terrifying looking, but you just got these expected frequencies. You're just taking a percentage of your sample to get your expected frequency. And the observed frequencies are just how many people did you get in every category, basically. Okay. So any questions about that? Okay. Now it is asking here, the expected frequencies based on the null hypothesis. Remember, the null hypothesis said P is 17%. So we're assuming it's true. And if it's true, then there should have been 68 boys with asthma. You follow? But there weren't. There were 88 observed. So it says the expected frequency just computed is based on the population proportion P from the null hypothesis. Is it similar to the observed frequency of 88? What do you think? Are those similar? That's almost that error is almost a third of the value of 68. So no, the answer is no. There's a big difference. Of course, it's sort of a matter of opinion, but what's a big difference? But I think it's pretty different. Okay, so now they're asking us to do this contribution to the chi-square statistic. So the O minus E, again, it was 88 kids observed, but there were 68 expected. You have to square that and divide by the expected frequency again, which was the 68. Okay? Unless I do in my head, that's 20 squared 400. So, and it says 4 places. I'm going to do 5 5 places after the decimal and be a little neurotic about it. 5.88. Anybody? What's the rest of this? 235, thank you. Okay, again, a little neurotic to be that precise, but remember, we're trying to show you how similar the chi-square test is from the Z test that we just did. Okay, now, kids without asthma. Remember, it's categorical. We've already looked at kids with asthma. Now the other category is kids without asthma. So it says, for the teens without asthma, give the observed and expected frequency. What's the observed number of teens without asthma? These are the failures in the binomial experiment. So again, there's 400 kids. Subtract out the 88 with asthma. And what's that? Okay, 312. Great. Now the expected number is n times q, which is the same as n times 1 minus p. Okay, so expected frequency is nq. N again is 400. Q, if you go way back to the top, we said Q was 0.83 here. So if 17% of kids have asthma, then 83% don't. And that's what we expect. And that's why right now, we are taking 83% of 400 because 83% should not have asthma. Okay. 3 through 3, wait a minute. Did I do that wrong? Oh. This one's off by 20 also. But does this seem like as big a miss as the other one? Are these similar? Again, this is a matter of opinion. To me, to be off by 20 depends on, if that's a big mistake, it sort of depends on the size of the number. These are much bigger numbers than the last ones. So now to be off by 20, it doesn't seem like as big a deal. And the chi-square statistic will reflect that. So is it similar? Well, it's I'm going to say it's sort of similar, but okay, and it's just based on the magnitude of the numbers. And you'll see how the chi-square statistic reflects this. So the observed frequency was 312. The expected frequency is 332. So again, that difference is 20, and when you square that, you get 400. So it's the same numerator, but the denominator is a bigger value. You're dividing by 332 to sort of get, it's almost like it's like a proportion. But let's see what we get. Again, we're going to do 5 places after the decimal. 1.20482, I agree. And this isn't, oops, this is a sort of, how should I say? This is a measure of deviation. How much does the observed frequency deviate from the expected frequency? And notice when we did the successes, this measure of deviation, which is the observed minus the expected, how different are they? Comes out at 5.88-ish in the first case, where we said there was a big difference. But now this measure of deviation for the failures, it's coming out as 1.20-ish, and that's just not as big a deal. So yeah, in that sense, the failures are, have less deviation between observed and expected. Okay. Now here's a difficult question. Again, so this is measuring deviation based on this null hypothesis. Remember, the null hypothesis says that P is 17%, and from that we were able to come up with this value. are these values, and this statistic, the expected frequencies, come from this. Okay, so the E's are based on this. Okay, so if the null hypothesis is false, then the assumption, this notion of using 17% is not valid, and yet we were using it. So it says, if the null hypothesis is false, would you expect the statistic to be small or large as we measure the difference between the observed frequencies and the expected frequencies that are based on an incorrect assumption? Small or large? We got one for each. When the difference is, okay, so if the null hypothesis is true, then what you expect, which is based on the null hypothesis, a true assumption, should be close to what you're observing because your expectations are based on proof. If the null hypothesis is true, the observed and the expected should be similar. And that makes, when the O is similar to the E, then when you subtract them, it should be close to 0. Okay, so your chi-square statistic comes out small when the null hypothesis is true. So if the null hypothesis is false, then the expected frequencies are going to be just wrong. They will not match up with reality. The O's and the E's should be very different, as we saw in the first case. Okay. If they're very different, when you subtract, you get a big number. That's just what it means to be different, right? And you get a big number, you square it, gets even bigger, and the chi-square statistic is just going to be large. Okay, I hope that makes sense. Okay, so because H0 false results in a large test statistic, okay, this means this will be a right tail test always. I don't even know what the distribution of the statistic looks like. I just know that this statistic goes to the right when the null hypothesis needs to be rejected. It only goes to the right, it never goes to the left. When the null hypothesis is false, I should say. Okay. All right, so that's interesting. On question 11, it says the observed number of teens with asthma was observed from a random sample and varies from sample to sample. The number of teens without asthma was determined by you. For a given sample, does this value vary freely or is it uniquely determined? Oh my Lord, that's a lot. Okay, let me just tell you, there are two observations here. And this is a degrees of freedom question, okay? The two observations are kids with asthma and kids without asthma. The question is, are they both random, given that you have 400 kids? Or is only one of them random? I'll say it again. You've got two observations, kids with asthma and kids without asthma. Altogether is 400 kids. Are both of those observations random? Or one of them random? Only one is random, correct. So remember, when we talk about the variability of a statistic, this chi-square statistic, we have to remember that the observed values are not all going to be random values. And the amount of randomness in a statistic determines the width of the probability distribution. More randomness implies a different width than when there is less randomness. Okay, so we will be talking about how many of the observed frequencies are random And that's a degrees of freedom question. You guys are saying there is only one random only one observation is random. It doesn't matter which one you call random. You tell me one, and I'll tell you the other. Okay, I only need to know one. Tell me how many successes there are, I'll tell you how many failures. Tell me how many failures there are, I'll tell you the number of successes. Okay, so it doesn't matter which one you think is random. The point is we're measuring how much randomness is in these observations, and that's the degrees of freedom question. And by the way, my screen is frozen. Okay, so here it says if the degrees of freedom represents the number of observed frequencies that vary independently or randomly, how many degrees of freedom are present among the two observed frequencies? We've already said the degrees of freedom will be 1 here. Okay, 2 observation, 1 is random. And you only need to tell me one of them and I'll know the other. Okay, is that clear, everybody? So it's gonna, in a chi-square test, the degrees of freedom is always the number of categories minus 1. Here there's 2 categories. I only need to be told one of them because I know that the total has to add up to 400. If there's 10 categories, then you have to tell me 9, and then I'll know the 10th. So it'll be the number of categories minus 1 for the degrees of freedom. Okay, any questions about that? Okay, so here I'm kind of just showing you how you would normally compute the chi-square statistics. So I have to go back and get all these numbers. So if I go all the way back, 88, 68. Okay, so observed frequency 88 kids with, but we expected 68 kids with asthma. And then the chi-square statistic for the first one was 5.88235. Okay. And then with the kids without asthma, I don't remember, 312 and 332. And then the chi-square contribution is 1.20482. Okay, then we have to add up the total contribution to the chi-square statistic. So this number here is chi-square, which is the sum of both of the O minus E square over E values. Okay, let's add those up. Okay, 7.08717, yeah, I agree. And I'm gonna go ahead and write the formula again down here. So it's the sum of O minus E squared divided by E. And what we got for that is 7.08717. Now it's telling me to round to 4 places. I'm not gonna, I don't know when, I don't let the cat out of the bag too early. I'll round it to 0872 now, fine. 4 places after the decimal. Okay. Oh, fine, I'm gonna keep the 17. I don't know what to do. Okay, now here it says in this question, we begin to understand the relationship between the z-score that we did before and the chi-square statistic that we just did. And it says it's asking us to compute the square of the z-score from question 3. All right, z squared is what they're asking for. Okay, so I have to go all the way back to question 3. Here's our z-score. 2.66217, super precise. Okay, gonna paste that in down here somewhere, there, and square it. So I got 7.08715. So I think at this point, I'm going to cheat just a little and say, okay, these are both 7.0872. Follow me here? The differences are because of rounding. And we have to round at some point. So that's why you see minor differences between these, but tiny, tiny differences. Okay, any questions? And the point is we want you to see these are the same. So the reason why we call chi-square and not just chi is because chi-square with 1 degree of freedom, notice, is related to the z statistic how? Yeah, chi-square is z squared. So chi-square is the distribution of squared z-scores. Oh, weird, right? All right, any questions? So this is this distribution, yeah, okay, so you're squaring some z-scores, which is a weird thing to do, and now we're going to find out probabilities for squared z-scores. Well, apparently we are. Okay. What happens when you square z-scores and then figure out the probabilities? Well, it depends on how many degrees of freedom there are. Okay, so let me go ahead and read this. First of all, let me pause for a second. Any questions about what we've done here? Okay, so when conducting the multinomial experiment with k outcomes per trial, the chi-square statistic here varies approximately according to the chi-square distribution. It's also approximate. Chi-square distribution is actually a more complicated distribution than just for it's not actually developed for multinomial experiments. It's actually for a continuous quantitative variable, but it's just a different discussion. You can also say that it varies approximately according to the chi-square distribution with k minus 1 degrees of freedom. Remember, k is the number of categories or outcomes per trial. Okay, so there's k minus 1 degrees of freedom. With 1 degree of freedom, which is what we're doing now, the chi-square distribution is the probability distribution of squared z-scores from the standard normal distribution. So you're just randomly selecting some value, computing the z-score, squaring it, and thinking about, okay, this is where this value lands. And you just do all these squared z-scores. You kind of make like a histogram of them, and the histogram looks like this. And it depends on the number of degrees of freedom. Okay. So it says with 1 degree of freedom, and I already said that. Oh yeah, one degree of freedom, you have the distribution of squared z-scores. But listen to this, with k minus 1 degrees of freedom, the chi-square distribution is the distribution of sums of k minus 1 squared z-scores. So you're doing a whole bunch of z-scores squared and adding them up. Okay, and k minus 1 is the number of random z-scores. Okay, so notice k minus 1 is the degrees of freedom. So the number of z-scores is the number of degrees of freedom, and they're all random z-scores, so randomly selected. So you don't even count, you don't even get a z-score for the non-random observation. We're only doing the number of z-scores that match the degrees of freedom. And so you can see the width of this distribution depends only on how much randomness is in your chi-square statistic, not how many outcomes are in your experiment. Okay. So because of this, the distribution only allows non-negative values. So that makes sense too, because these are sums of squared z-squares. It can never be negative. Several chi-square curves are plotted below with varying degrees of freedom. So it's kind of cool looking. I don't know if you can see, these are all skewed to the right. 8 degrees of freedom is here. It's looking more bell-shaped, and it is possible to show that chi-square distributions get very wide, but they also approach normality. But you need the degrees of freedom to be big enough so that you get a left tail and a right tail. And it has to be pretty big because the distribution gets so wide and low, as you can see is happening here. But eventually it becomes essentially symmetric. And you can use the normal distribution to approximate the chi-square distribution with large degrees of freedom. Okay, I don't know how large. I know some people have studied that. Okay, any questions? Okay, so it says, the chi-square hypothesis test which we are conducting is always a right-tailed test, as we've discussed. So the p-value is the area to the right of the test statistic. We can, and for some reason I did not finish that sentence. So that's interesting. The chi-square distribution with 1 degree of freedom is plotted below. I wonder what I would have said. The chi-square distribution with 1 degree of freedom is plotted below. The 1 degree of freedom graph is quite strange looking. It has a vertical asymptote, which is crazy for a probability distribution. Now remember, the total area under a probability curve is still 1. So the probabilities are not infinite, but the curve goes infinite. So you can have curves that have skinny little slices that go up forever, but they're so skinny that they don't amount to much. Okay, the total area is still 1, even though it goes up forever there. It's just a tiny sliver. So the shaded area to the right of the test statistic is a p-value. Take some time with your instructor to learn how to find such p-values using technology. Okay, so what I'm going to do for you guys here is I'll post this. I didn't think to do it last night, but I'll post this page that I put together for you in Desmos. So I'm just going to hop over to Desmos again real quick. And so what I put together, let me find my chi-square. Here it is. Open. And this is super cool because it's got a slider for the degrees of freedom. Just totally interesting how Desmos allows you to do stuff like this. So we're doing 1 degree of freedom. So you can see how it gets real pointy, and then eventually it gets an asymptote with 1 degree of freedom, like that, a vertical asymptote. Okay, and then we have to key in our chi-square statistic, which was there, it was 2 point, I'm going to do the more, let's do the 2.08717, which we got, okay. What was it? I think I'm confused. I'm certain I'm confused. 7.08717. So I hope that's right. Okay, so you do that, and I don't know if you can see, there's a tiny sliver that's shaded in there, just to the right of 7. Okay, any questions? Okay, 0.00776 is what we'll say. I think that's what I got. Yeah. Okay. So that's our p-value. And so I'll just make a note here. This will be a chi-square p-value calculator on Desmos. Sorry, well, I'll put a link to it on Canvas, so you can use my little page for that. Okay, so p-value is 0.00776. And then it says, how does the p-value compare to the one in question 4? Now, there's going to be a difference, and I want you guys to figure out why they're different. Okay? So we're going to go all the way back to question 4. What's this all about? We got 0.00388. Why is it different? You guys know. You know why it's different. Think about it. Everything you need to know is what you're looking at here. Why is the p-value wrong? Are you awake? Maybe you're angry. I'm sure that's what it is. Dang it. Number of tails. What do you mean, Andrea?
Doesn't one have 2 and the other one is only 1?
Yeah, the chi-square test is always a one-tail test, but here, this equivalent test, we should have doubled the p-value. So this is actually the wrong p-value, right? So let's change our notes a little bit here. It's not the p-value. That's the area of the tail. Okay, so this is how I'm changing this. It is correct, and that is the area of the tail, but the p-value should have been 2 times that, 0.00388. So what's that? Right, 0.00776. Now, is that the same p-value? Now that we did it, right? .00776. It's identical. Okay. So how does it compare? These are identical. Okay, so it's like, see, with the chi-square test, you're squaring the z-score. So the negatives and the positive all end up on the right side, which has the effect of doubling the p-value. So I had to compare this to a two-tailed test because, again, the chi-square is effectively a two-tailed test because the left and right z-scores, the negatives and the positive, both go to the right side when you square them. So you get both tails in one, and it sort of doubles your areas. And that's like a two-tailed test. Any questions about that? Kind of weird, but totally makes sense to me anyway. Of course, it makes sense to me. Any questions? So they want us to sort of draw this. Oh, critical value. Okay, they want a right tail critical value on table A4. Okay, so let's see, table A4. I don't know, I'm gonna have to go out of this. Here's table A4. Look at that thing. Now, the good news is only 1 degree of freedom. And I don't know if you remember, but it was an alpha of 0.01 on this one. Okay. And it was 1 degree of freedom, so we can go all the way down to that. Okay. So that's table A4 again, chi-square distribution, critical values. There is no table for chi-square distribution p-values, and the explanation is complicated. It was impossible to make a table that's not hundreds. Basically, if you make a table for chi-square p-values, you basically need a page for every degree of freedom, and that's just impossible. So you just can't make a table for chi-square p-values. You gotta use technology for that. All right, so that's our the critical value, 6.6349. So let's hop back, 6.6349. Okay, and so the tail here, alpha is 0.01. That's a critical value. Okay, any questions? And does it ask us to compare to the other Z critical value? So let's look at the Z critical value. I think it was 2.576. Let's just double check that. Here it is here. 2.576. Okay. So now we're taking that value. Where am I? Here we go. 2.576 and squaring this, the Z squared, 2.576 squared. Anybody? This is not as good because of all the rounding. Yeah, I'm going to just say 6.635 to show you that with 3 places after the decimal, that's the same as 6.635 down here with 3 places after the decimal. Okay, so again, I want to just point out that the chi-square critical value is equal to the Z square critical value. Okay. And again, the differences are because of rounding, the rounding that we do as we go through. And the table's values are rounded as well. No way around it. Get it? It's just funny. You're all good? So what should we conclude? Well, again, the p-value was 0.00776. Yeah. 776, which is less than 0.01. That's our alpha. And so we reject the null hypothesis as before. Okay, so again, the tests are equivalent. Same p-value. They're the same. They are the same hypothesis test with a completely different set of tools, but they yield the same p-values. And it shows you, these distributions are connected. The chi-square distribution is derived from the Z distribution. It's assuming you have these Z scores from a normal distribution and that you're squaring them. So obviously there has to be a connection between the two. Okay. All right, so I'm just waiting for questions. I'm not going to write a new conclusion. It's the same conclusion in context, about boys with asthma. Okay, so the next, I hope that example allows you to transition easily to more than 2 categories. right? You've done 2 categories, now you got to do more than 2. It totally makes sense. It's a little tricky because you have to have a proportion for every category. Right now, the proportions were P and Q, right? The proportion of successes and the proportion of failures. That's 2 proportions for 2 categories. If there are 3 proportions, then, sorry, 3 categories, then you need 3 proportions, and they have to add up to 100%. Right? If there's 4 categories, then you need 4 proportions, and they have to add up to 100%. Because they all together, and they make 100% of your data. Right, so anyway, let's just do our quick little summary here, and we'll go on. It says, in summary, because the z-test for a population proportion yields the same p-value as the corresponding chi-square test with 1 degree of freedom, the tests are equivalent. So why use a chi-square test? The answer is because it allows more than 2 outcomes per trial. It's actually more useful than the z-test. The z-test only works for binomial experiments, but the chi-square test can be applied to multinomial experiments where more than 2 outcomes per trial are possible. So generally speaking, if it's categorical data, categories just mean multinomial, right? And multinomial just means chi-square. Okay. So now we outline a process for chi-square tests in a multinomial experiment, and these are often referred to as goodness of fit tests. And what you're doing is you're trying to measure how good the observed frequencies fit to the expected frequencies, and so that's why it's called goodness of fit. Okay, the goodness of fit test makes claims about the proportions or probabilities for each outcome of a multinomial experiment. If there are k outcomes per trial, then the null hypothesis would be this monstrosity here. You have to give not just the p and the q, you follow me? You've got a bunch of proportions and 1 for every category. So there are k categories, so you have to have k proportions. So there's a p with a little k subscript, just to indicate there's k of them, okay? And you're giving a value for each of these proportions. That's a lot, okay? Because the sum of all the probabilities in a distribution is always 1, the hypothetical proportions have to add up to 1, which means if you tell me k minus 1 of them, I'll be able to tell you the last one, right? So that kind of sounds like a degree of freedom issue as well. It really isn't, but it reminds you of it, okay? The alternative hypothesis would be well, for the null hypothesis to not be true. 1 or more of the proportions would be incorrect. They don't have to all be wrong. Only one of them has to be wrong. So your alternative hypothesis is at least one of the proportions is incorrect. I'll probably say they're not all correct in the conclusion, so I'm not saying at least one. Somehow that to me seems a little confusing. Actually, let's fix this, the proportions are not all correct is a better way of saying that, I think. Okay. Any questions? Okay, let's go ahead and read this part, going through the steps. It says, using a sample of n independent trials, each having k outcomes, the experiment is conducted. For each outcome, the observed frequency O is the number of successes. The sum of the k observed frequencies is always the sample size. So the sample size is the sum of the observed frequencies. So the last observed frequency is not random. There are therefore k minus 1 degrees of freedom among the observed frequencies. Any questions? We already talked about that. Okay. Next, we compute the expected frequencies for each outcome. As with the binomial experiment, the expected number of successes is always NP, where N is the number of trials, the sample size, and P is the hypothetical proportion for the corresponding outcome in the null hypothesis. So you'll just do N times P for every category, but the P keeps changing, right? There's a P1 and a P2 and so on. Any question about that? It's pretty straightforward. For approximate normality in a binomial experiment, we require the expected number of successes and failures to be at least 10. Expected number of successes is NP. Expected number of failures is NQ. In the multinomial experiment, we softened this because with potentially many categories and multinomial categories, it can require unreasonably large sample sizes to get at least 10 in every category, because you're spreading your data out thinner and thinner. If you're following me on this, the more categories you have, the harder it is to fill them up with 10 values. So they soften the blow. We assume that the test statistic is approximately distributed according to a chi-square distribution, which assumes all the individual, I don't want to go into that. So it satisfies the chi-square distribution if each expected frequency is at least 5, okay? And the expected frequencies are always n times p. So you can write this as np is at least 5. Before we said np is at least 5, and the other np was actually nq. Had to be at least 10. I'm sorry, NP and NPQ had to be at least 10. Now we soften just to make life better, and they have to be at least 5. Okay, any questions? Okay, but that's for every category. A little bit of pain. But you have to compute all those anyway. Okay, step 3, assess the evidence. Chi-square statistic is this thing. The null hypothesis, and we've already done it, so this should not be a big deal. The null hypothesis gives probabilities for each outcome, and from these, we compute expected frequencies. If the null hypothesis is false, the test statistic should be large, as we talked about, because the observed frequencies will be quite different from the expected frequencies, so the differences, O minus E, will be large. This is why the goodness of fit is always a right-tailed test. When the null hypothesis is false, the test statistic should be large. Chi-square critical values are found on table A4 using k minus 1 degrees of freedom, where k is the number of categories. That's different from the sample sizes. So you have to, in these last sections, you have to keep track of the number of categories and the sample sizes. So it's a little pain. Okay, they're different things. So make a conclusion is your last step. When a test statistic falls in the right tail of the distribution, which is greater than a critical value, we reject the null hypothesis and support the alternative. Okay, this is one of my favorite problems all year in the article. Is there a season for homicide? From a really old magazine that I got references for. The article gave seasons in which 1,361 randomly selected homicides were committed. These values are summarized below. So these are the murders of those homicides, those murders. They've listed them by season. They don't look very different, but to me, it seems like the numbers are a little higher in the summer. See that? And people always say the murder rates go up in the summer. I don't know if it's true or not, but these are real data from some time ago. Okay, so we're testing a claim at 5% that the proportions for homicides are not equal. Well, actually, our null hypothesis is going to be that they are equal, but you'll see that in a second. So for K, how many categories are there? Okay, 4 categories. Thank you. Now, the null hypothesis is going to be basically all proportions are the same. And that's just like we always say, p equals some number. What will be the proportions if they were hypothetically, if they were all the same? Remember, they have to add up to a certain number. Yeah, they have to all be 0.25. Each E must be 0.25. So we're just taking 1 over the number of categories, 1/4 is 0.25. So each one of these, we're saying 25%. Okay, and the alternative hypothesis, oops, H 1 would just be these are not all correct, so not all the proportions are 25%. Okay, any questions about that? So that's the biggest difference now, is just how do you phrase a null hypothesis when you have so many things being tested at once. Any questions? Now, the sample size, we've got the number of categories. Remind you, K is 4. That's the number of categories. But that's different from the sample size. The sample size would be the number of observed frequencies. So if we had gone up to this table and added all this up here to get a total, they tell us what it is. So the total is 1361. So I think that's the sum of these. Okay, so I don't think we need to compute that. 1361 we can put in as our sample size. If they don't tell you, you have to add the observed frequencies up. Okay, any questions? Okay, so remember the expected frequencies are E, which are all in P. So the N is 1361, and in each case the P is 0.25. So the expected frequency is going to be the same for every category. Okay, does that make sense? I think you get 340.25 here. Okay. And then they're all going to be 340.25. And if you add those up, they add up to the 1361. Okay, both rows of numbers, the observed and the expected, should add up to your total number of people. Murders. Any questions? Now the criteria, remember, is that each expected frequency has to be at least 5. So here we have satisfied that. Yes. Each E is greater than or equal to 5. Okay, any questions? This is fun, right? Couldn't imagine anything better than being quarantined, stay at home orders, doing chi-square tests. I love this kind of stuff. It's almost like when I go to heaven, if, that's the big question, if I go to heaven, God's going to give me an iPad and one of these sexy Apple styluses, and I'm going to sit around and prove math stuff all day long in heaven. That's what I'm going to do. K minus 1 degrees of freedom. You guys said there are 4 categories, so that's only 3 degrees of freedom. So the idea is you tell me how many murders there were in each of 3 seasons, but the 4th season you could figure out on your own if I gave you 3 of them. Yeah, the new iPad for sure. Yeah. That's hell for some people. It's different, isn't it? For some people, it's hell. Some people's hell is other people's heaven. I have to think about that for a bit. Everybody okay? So we have to do this computation, unfortunately. So we got to put all these, I'm going to copy all these expected frequencies over. Okay, so this is where this is the diciest part of the chi-square test, is it's kind of computation heavy. I mean, once you've done one, you've done them all. But yeah. So again, this first one, I'll write down what you're typing in on your calculator. Put it in parentheses, so 328 minus 340.25, close parentheses and square, and then put that over 340.25. And honestly, I don't know if you remember, but once you do one of these, well, hang on, I'll do one of these. Okay, so I got 0.4410 on the first one. And then if you use keep your direction pad on your calculator and highlight the computation, not the result, highlight the computation and press enter, you can go back and edit it. And you only need to change the observed frequency because the expected frequencies are all the same. Does that make sense? I would show you, but with one hand, I am no longer showing calculators anymore in my lectures. But I'm playing the pity card as much as possible. So that's a new feature to the lectures. Okay, so you can just repeatedly edit this if that's how you're doing it. Okay, well, let's fill the rest of this out. Now I'm hoping you guys are checking me as I go. 1148, I think. I don't have solutions in front of me. I'm working these just like you guys are. Because I'm wondering, could somebody tell me the last one? Oh, these are not coming up. My bad. There you go. I'm leaving the last one blank. Okay, 51. Yeah, exactly. 5160. Thank you. All right, and then can somebody just give me a yes or no on the rest of these numbers? If you agree with all of them. Okay, great. Thanks, Andreas. And then let's add these up. Oh. That's not what I got. That's what I got. 4.0345. Just so you guys know, on the final, we're getting really close, right? And so on the final, what I did here is I filled out most of the table. And then what I'll do is I'll just have you fill in a couple of the numbers here. I'm not going to make you do all of this. It's a bit much. Okay, but I want to see that you understand basically what's going on. So I'm not going to leave you out dangling on problems like this where there's tons of computations. I'll do some, and then your job is maybe to add it all up, or compute one or two, or maybe one, and then add them all up. So that's a chi-square statistic. It is this sum that we just did. .0345. Okay, any questions? Everybody okay? Now this thing, the next one's asking for the critical value. Okay. So I don't remember what our alpha is on this one, so let's look it up real quick. Somewhere when it talks about the homicides. Here we go. 5% right here. Okay, so our alpha is a 0.05. I'll just go ahead and map out the way the table works. So look for your 0.05 alpha, and degrees of freedom, remember, are k minus 1. There were 4 categories, so this is 3 degrees of freedom, like that. Okay. So let's bring up the table real quick. Okay, so again, these are critical values. 3 degrees of freedom, 0.05. Okay. How's that look, you guys? 7.8147. Any questions? 7.8147. All right, let's pop back. Okay, 7.8. Okay, so that's close to 8. So the 7.8147 is our critical value. And the area of the tail is alpha. This looks a little fatter this time with our alpha larger. So this one had an alpha of 0.05. Okay, any questions? Now notice the 4.0345 does not land in the tail. Okay, so it's over here. That's the test stat. So we will not be rejecting the null hypothesis. So you can say it here, do not reject null hypothesis on this because the test stat is not in the tail. The tail, which begins at 7.8147, which is our critical value. Okay. Now they want us to do it again, but this time we're supposed to get a p-value going. So chi-square distribution is positive because you're squaring z-scores, remember? It starts at 0. Okay, our test statistic was kind of low. It was 4.0345. Okay, so that makes the p-value kind of big. Use technology to determine the p-value. Got it. Remember, its degrees of freedom is 3. Okay. Any questions? Okay, we're going to use technology. So just change. I'm going back to that Desmos sheet. Again, I'll post this on Canvas with the other p-value calculators. Degrees of freedom needs to be set to 3. Oh, by the way, if you ever screw up, I see how I screwed this up. If you ever screw something up in Desmos, okay, I've screwed it up. Then you want, there we go. You can reload the page. It's easy to delete something on here. All of these symbols can be edited. You know, I forgot what my chi-square statistic was, but what are you guys at for 4.0345? Let me zoom out on this so you can see this distribution. 4.0345, right? Yeah. Okay. So you get a nice, Desmos is nice because it gives you a graph of the situation. Looks just like the one we drew. And the p-value is 0.2578, so that's a huge p-value. Okay, any questions about Desmos? Okay, 0.2578, got it. And just as a reminder, when you look back in the notes, the p-value calculator. Oops. For chi-square distribution is on Canvas, and I'll get that up after class. All right. Again, the p-value this time, 0.2578. This one's bigger than the 0.05, which is our alpha, which means we're going to fail to reject the null hypothesis. Which said each proportion is 25%. Okay, so we can't reject that. So we won't be able to support the alternative. So I'm going to just copy what I wrote down here. Oops. Now, remember, failing to reject it is different from saying it's true. So we never support the null hypothesis. We just say we can't reject it. Okay? But here, and you can only support the alternative, and we do support the alternative when you reject the null, but we didn't, so we can't. Okay, so we don't support the alternative. H1, which said the proportions aren't all 25%. So we can't support that. And remember, it's a little confusing, but what they had said was, is there a season for homicide? That was the title of the article. Okay, I'm going to pause for a second. Susan, I don't know what you're asking. Is this p-value, I-value? Oh, are you being funny? I don't know if you're being funny. It does it for you. It's built in. So, and you know what, you guys, I really should have given you this link. So let me see if I can share this with you. Okay, so presumably that would have worked. So if you want that link right now, I'm so sorry. I should have done this before. So how do I do that? I can't do that on my, hang on. I have to do this on my Windows or my on my desktop. So I'm going back into desk notes here. And I know you're ready to keel over for a break. Okay, guys, I'm pasting the link to this p-value calculator for chi-square. So you can click on that and it'll launch the page that I'm showing you right now. Go ahead, try this out. Put in the 3 degrees of freedom. Was it 4.034 for the statistic? Susan says, does it include squaring for right tail? Yeah, it does. It's built in. Yeah, you don't square anything. It's a distribution of z-scores already squared. So that was just to show you, when we were squaring z-scores, I was just trying to show you what the chi-square distribution is. Okay, we are using it now. It is a distribution of squared z-scores added together. But you just let it go. Okay? You don't have to think about that anymore. The main point is to see how closely related the chi-square is to the normal distribution. So I'm just giving you a second to type all this in. I'll make sure I got these numbers right. 4.0345 is really what I should have put in. So I'm going to tweak my chi-square a little bit. I should change the area. 2578 is the correct p-value. I told you guys I was having surgery on Monday, which means I have to take every phone call. So I'm going to put you on hold real quick. Okay, sorry about that, you guys. All right, so let's quickly, I just got my check-in time for the hospital on Monday. All right, just real quickly, let's wrap this thing up. Did I get the right p-value here? 0.2578. Actually, that matches what I wrote here, so that's fine. Okay, all is good. And then we'll say the data do not support the claim. That murders occur I'm just going to say in different proportions. Depending on the season. Does that make sense? So they're claiming, yeah, or the question is there a season for homicide? And again, there's always this question of, do we need to sort of be prepared for more murders in the summer? And based on these data, what you would say is, yes, during this period of time, it was higher in the summer, but it's not statistically significant. And when it's not significant, it's just this random thing. So you can't count on it happening again if there's no sort of fundamental difference, and we haven't proven a fundamental difference. So you wouldn't think, okay, we need to staff up more or police in a different way in the summer until we had hard evidence that summer really was a problem. And this is not hard evidence. It's not to say it's not true. It's just that we don't have evidence for it. Okay, so I'm sorry to make you guys, sorry for the interruption. I know it's been a long time, so I need to give you a break. Let's take a 10, let's go till 10:40, and then we'll see if we can squeeze in 2 more sections after that. Actually, yeah, there's 2 more after that. They're quicker though. All right, see you guys in a minute.